I'll be presenting a report on the size effect on shear capacity of lightly reinforced concrete beams. Here is a basic outline of the report. I'll start with the definitions and mechanism involved in size effect. Then I will show the evidence of size effect in reinforced concrete beams from various experimental investigations. I'll show the applications of those experimental investigations in present-day design codes and previous design codes. I'll also show the changes that have been made in the latest design provisions which have incorporated the effect of size in the design of reinforced concrete beams. I'll finally finish with the conclusions. Size effect is a common phenomenon that is seen in brittle materials. Because concrete is also a brittle material, it is also expected to exhibit size effect. When size effect is prominent, crack initiation load is not proportional to the ultimate load. Since in concrete, we expect that the ultimate load is reached at the same time, uh, this may lead to unconservative design if the size effect is not taken into consideration. If we consider the nominal stress at failure of any structural member given by sigma n equals to Cn into Pu by Bd, where sigma n is the nominal stress of a section, Cn is a constant of proportionality, Pu is the ultimate load at failure, and B and D are the dimensions of the section. If for two geometrically similar members uh, of different sizes sigma n is same, then we can say that size effect does not exist. However, uh, this this could be similar to two beams having same which are geometrically similar, say rectangular beams, but having different depth. If they both fail at exactly the same shear stress, we can say that size effect does not exist. However, in case of concrete, this would actually mean that the failure occurs simultaneously throughout the section. However, in case of concrete, failure does not happen simultaneously as soon as the crack forms. Rather, failure propagates slowly after the crack is formed before finally leading to ultimate rupture of the section. Bazant and Kazim size effect in reinforced concrete beams. They took a number of different beams of different sizes and having different reinforcement ratios, and showed that as the depth of the sections increased, uh, the stress at failure would decrease. Here, Vc by Vu is the concrete strength to the concrete stress at ultimate failure of the section. As we can see, as the value of Vu increases, this value will start decreasing. At smaller values of D, we will have larger values of Vu, which means that at smaller values, at shallower sections, we will have larger shear strength. Thus, they were able to prove that the size effect does exist in case of lightly reinforced concrete beams. Bazant in 1984 had proposed an equation for which could be used to represent the size effect and which needed to be calibrated. Uh, it was concluded from this work that a strong correlation exists between the size of a member and the shear strength of a concrete beam, and uh, he proposed changes to the existing ACI code at that time. Since uh, uh, since Bazant recommended that the ACI provisions needed to be revised, Angelakos in 2001 performed a series of tests on 21 large beams. The original test by Bazant was performed on smaller beams, so These tests were intended to confirm whether or not there was an actual need to change the provisions with respect to shear strength of concrete beams. A comparison was also made to the ASTRO LRFD provisions. Uh, Here, the shows the results for one of the lightly reinforced concrete beams. Here we can see that as the depth of the beam is increasing, our the strength, the shear stress at failure of the beam is of the experimental results, as we can see here, shows a declining trend. However, this could not be predicted by the ACI provisions, as this was not incorporated into the ACI code then. However, if we look at the ASTRO provisions, this was incorporated there, and we can see that a downward trend is predicted by the ASTRO provisions. However, it is interesting to note that although there is a change in concrete strength here, for example, there are two concrete strengths that have been taken, one 37 MPa concrete and one 99 MPa concrete. A change, or rather a increase in strength is expected by the ASTRO provisions. However, if we look at the experimental results obtained here, Bn represents the normal weight concrete and normal strength concrete, and the Bh represents the high strength concrete. After a particular depth is reached, the shear strength is no longer influenced by the depth, by rather the strength of concrete. Here we can see that three sets of experiments have been performed with different reinforcement ratios. As the reinforcement ratio increases, an upward trend is seen in the strength of concrete beam, as seen here. Similarly, if we increase the concrete strength, it is observed that not much variation is seen in the shear strength of the member. However, this was completely unconservatively predicted by the ACI code. The ACI code predicted that at higher strengths of concrete, higher shear strength of the member would result. However, this was not true. Also, in case of the ACI code, not much variation is seen as the reinforcement ratio varies. However, this was a significant variation can be seen in the actual test results with respect to different reinforcement ratios. Uh, it can be seen here that the ASTRO provisions were much better in prediction of the shear strength of the members compared to the ACI provisions. The series of experiments that were performed by Bazant and Kazemi in 1991, which I have discussed previously, were again repeated by Benz and Buckley in 2006, as some of the results obtained were found to be inconsistent with the experiments that were performed later after Bazant and Kazemi in 1991. He found that the beams, using the same sections and the same properties, he found that the beams failed at shear stresses 31% to 70% higher than the previous 1991 experiments. Uh, also the crack patterns were observed to scale with the size of the beams, as he had scaled the experiment up to some degree compared to the previous experiments. The shear strength of the beam was found to be higher than predicted by the ACI code, which was against the argument provided by Bazant and Kazemi in 1991. Also, he finally argued that the size effect, although it does occur, but is not prominent enough to warrant a change in the shear provisions. Bazant et al. In 2007 compiled a number of series of experiments performed previously and created a database of 398 beams. This database was used to calibrate the equation he had proposed previously. He finally proposed an equation to find VC, which incorporated the effect of depth of the beam in and took it into consideration in finding the shear strength of the beam. Here the equation is shown. And this equation I'll use it later to solve a problem. Uh, the detailed formula was also simplified to be used as an alternative. Here he kept a cutoff of 6 inches as the depth at which the size effect should be started or should be taken into consideration. Here the first simplified formula is the original formula that was there in the ACI code, and he proposed a modification to this formula when the code when the depth is greater than 6 inches. This modification can also be seen here, that when the most of the experimental results that is seen is actually above Vc equals to 2 root over f dash c, uh, which was the original formula. Based on the studies that I have discussed previously, a number of changes were proposed to the shear design provisions and were adopted in subsequent codes. The latest revision to the ACI 318 provision includes a formula for calculating the shear stress specifically for a beam which has less than the required reinforcement. This incorporated the size effect on the shear strength of the beam. Before I get into the changes, I wanted to discuss the uh, original or rather the previous formulas that were used for finding the shear strength of a member. Here, there were two methods in the previous version of the code, which was the simplified method and the detailed method. The simplified method was the same provision which had been used since a long time, whereas the detailed method also considers the effect of rho w, that is the reinforcement ratio, and the vu and mu acting at the section. However, it was found that uh, if we in the earlier version of ACI, although both rho w and mu are taken into account, even if we double or changed rho w and mw by a certain factor and keep everything else constant, it has no effect on the shear resistance. In the current code, this was changed, and shear resistance was made proportional to rho w to the power 1 by 3. The uh, the size effect factor was introduced in the current code. Here we can see lambda s is equal to 2 by divided by 1 plus d by 10, which is similar to the equation that was initially proposed by Bazant. Also, this lambda s is incorporated into the equation for finding the shear contribution of concrete. Kuchma et al. In 2019 studied the suitability of the current formula in predicting the strength of a section upon varying the depth of the section and varying the concrete strength. Here it can be seen that even though we have a wide range of depths and wide range of concrete strengths, but there is no particularly downward trend with respect to the change with respect to the strength ratio. That is that is the strength shown by the test to the ratio of the strength shown by the test to the predicted strength. Thus, we can say that the formula is suitable for a wide range of beams. Finally, the following conclusions can be made with respect to the size effect on lightly reinforced concrete members. The experimental studies presented in this report show that large and lightly reinforced members show the size effect. Increase in depth and reduction in shear reinforcements and longitudinal reinforcements amplify this effect. This effect was not considered in the previous iterations of the ACI code, which may have led to inadequate margins of safety in such cases. Size effect also exacerbated with increase in concrete strength. However, it is observed that the trend is only prominent for very high strength structures, and no change was made to address this in the latest revision. Thank you.